Okay, so next I will show you using Paraview to realize CFD results. So this is the main user interface of Paraview. So as all its function is listed in this menu bar, and also this is the red hand here is the main places to show this visualization area, and here are some very common functionality buttons that can we can either click the function here or selecting them through this main menus. So the first step usually is just load this VTK files or VTU files. So um, this morning I already um, prepared some VTK files. So here in this window, you can see I have a lot of VTU files, and these VTU files are the real results of safety data. And besides these VTU files, you can also may find these PVTU files, and this is actually a header file that because these VTU files can be processed in parallel, that each process generates its own VTU files and numbered by this P number. So in this case, there's only P0, which means the VTU files is only coming from one CPU. And in some cases, you may get VTU files from several processes, and the file from each process is indicated by this different number of P here. Can be so. For example, you may get simulation P000 or simulation P001, but it's actually belongs to the same data in the same time frame, and so this all the file name of from different process will be saved in this VTU. So right now I will first show you um, realization using only a single file from a single time step, and later on I will use this PVD file that I will load this all the data from different time steps to show you how to visualize the results over time. So right now I just load one VTU files, example here, this one, click OK. And here after load we have to click this apply button. Then in this right window we actually see this um, our mesh domain, and also we can see here it represents the pressure value on this whole domain. This is a so-called channel flow around the cylinder, and the flow is flowing from left to right, and this cylinder is because this cylinder is a solid obstacle and no fluid can through this area. And after loading, we saw already here this pressure distribution across this whole domain. And indeed, it's a 3D object normally, but in this case, and also in this lecture, you will mainly doing 2D simulation, so I also only show you 2D cases. But remember, this 2D is just a plane that in 3D domains. And also here, this we can choose different variables we want to visualize. So for example, here pressure is also selected, and also we may choose to display the velocity distribution along this fluid domain. And here this, because velocity is a vector, so we can choose either the magnitude of the velocity, or we can display individual components of velocity vector component. And also we can select this solid color. It use the same color for all the domain. And here this surface with edges, we can use this option to realize our mesh, because we are using voxel meshes, so we can see. So have a closer look at the region near the sphere. So you can see we are using voxel elements. Each element has the same size, and using these voxel meshes to represent this sphere, a cylinder in this case. And also this, one can use this mouse to rotate the geometry, and also to right click to move its position, and also to magnify or zoom in, zoom out. So by using this surface with edges, we can realize the mesh. And so let's go back to pressure distribution. The screen is a little bit small, so some buttons are hiding. And also there are some buttons to set the view of this fluid domain. So for example, we have this set view direction from Z axis, so it will reset the view to in that direction. And also there are several views of set in X direction or Y direction. So in Y direction it's just a plane, hardly to see here. So we just use this Z direction. And so also from this figure we can see there's also a color legend to represent which color represent which values on this fluid domain. Of course, we can change here this data range is automatically set to be maximum value and minimum value of the whole domain. And of course, we can change the data range by selecting this set range, this force button here, to set whatever values we want. So in some cases, we may change the value to get a better view of, for example, in values on different regions. So rescaled, so we can get a better view of how the value is changing on, for example, this area. And also we can change there are several color scheme we can change, we can choose. So the common one is this cool to from blue to red, and also this one. So also we can select the grade scale, which is black and white. But the most common one we use is normally this rainbow color legend. Also for this color map, we have We can use log scale to represent the color. And this log scale can only apply to value that's positive, but in this case we have some value is negative, so it generates something not very meaningful. And also one can select this data range in this table. So right now we just fix ourselves to this rainbow color map and select the automatic data range. So setting max and minimum automatically. Arrange it. Um, Also, there are several useful functions that we can visualize display a part of the domain. For example, we can click this here, this function called clip. Second. So by using this clip, one can set up a plane, and we can display only the content in one side of this plane. So right now we have this plane that of x normal, and we can apply it so it only display the normal side of this plane. So in this case it's right side, but we can change the normal of the plane so it will display the other side of this plane. And if we don't need a specific functions, we can use this delete button so it will delete this clip and display the original fluid domain. Yeah. And another very important step is that called slice. So the slice it will create a slice, and only results on this slice will be uh, displayed. And because you will do the simulation in 2D, and also uh, though in 2D right now this fluid domain is still consists of elements, so there is a small size of element in that direction. So a better way to realize this domain in 2D is to create a slice in that direction. So in this case, um, there's no length in that direction. So you can so it's not very clear from this projector, but later on, I would suggest you also use this slice to give a get a better realization effect. And after having this slice, another type is to change this uh, important step is to this cell data to point data, because right now this RVT file is displaying the result for voxel elements and this is called cell data in the context of Paraview, and we need to convert this cell data to point data, and can be done by selecting in this filter alphabetical cell data to point data. And then we can create this different types of plots that I show you in my presentation today. So for example, the first one is called glyph. It's actually vector plot. So we can choose, there are several different types of vector. We can either use arrow or box or cylinder. And in this case, I choose this 2D graph. And also there are several functions to, for example, how to determine the size of this vector. So if we don't choose anything, we can first apply it. But the resulting vector is kind of too large. So we have to select a small scale factor. And in this case, you can choose this value. So right now I only display the vector of velocity, not velocity, because here I choose still pressure. So we can change it to velocity. So the color of the vector is represented by velocity x component. And because our original mesh consists a lot of elements, and in some cases it may be very slow, and we want to get a general distribution of the whole domain, so we may choose only display the values on every tenth or fifth points. So in this case, I choose tenths. If I choose 1 or 2, it will display too many vectors, kind of. Also, in this case, okay, but sometimes if the data is large, it will become a little bit slow. So normally I can choose 10 or fifths. And also one can choose a different opacity if we want to view this vector together with, for example, pressure distribution. Yeah, and also we can show axis of this whole domain. Okay, so this is vector plot showing velocity vectors in 2D. Another is this contour plot. So right now it's showing this pressure distribution over the whole domain. If we want to show the contour line, and here is we can click this button, contour, and we can select only scalar value, and in this case we only have pressure. And the contour, because the data contour only display contour lines on a certain number of values. So here, by default, it chooses an arbitrary value, but we have to create the how many contour lines we want to display. So in this case, we just choose time step of 10. So it will display contour line that on each line it will have a constant value. For other options, I guess we don't need to set, so apply. So here it displays different contour lines that along each line the pressure value is constant. And so in this case also we can also display this pressure distribution together with this contour line to get a better idea of the pressure distribution. So also actually we can also uh, so so the different contour or pressure distribution is determined by this pipeline browser. So this is um, just the distribution, and this click here. This this box controls this contour property. So if we want to change property contour, we have to first click contour here, then change its property. Yeah, so this is about contour. And also another is streamline. So we can click here this streamline tracer. It will create streamline based on this point data here. So first we have to set up its property. So the idea of this streamline that if the Paraview will starting from one point or several point and join the line that starting from that point and along this vector, a velocity vector. And here we can normally choose this high resolution line resources. And in this case, we choose Yx, so it's a line across the channel, and we can use mouse to change the position of this line, but here it's not very convenient. Let me do it again. Yx, here, and apply. So okay, it's actually, let me zoom in a little bit. It's actually becoming line and not voxel anymore. So I mean, I choose 100 line, so maybe I decrease this number, you get better view. Yeah. So in this case, the whole domain is represented by streamlines. So by streamline, we can get a better idea of how the fluid is flowing from inlet to outlet. And also we can change the color of the streamlines, for example, by velocity magnitude or by pressure values. After, also we can change the position of the color map. And after creating this streamline, we can save it as a picture. So we can select the export scene from this file menu. So it will create a snapshot of this figure in this EPS or other format. But EPS is a better format that without any loss of detail. So we can give it name and save it some places. For example, I can streamline channel cylinder and choose a position to save it. Yeah. Uh, another so also Paraview can plot the values of this XY plot. So we can choose the data analysis menu here and choose plot over line. So in this case, Paraview will let you to set up a line that it will plot the values along this line. So this line, for example, we can choose it to be yx and move its position a little bit and select how many points on this line we want to track, and yeah, apply it. So Paraview automatically open another window and shows the value that across along this line. And because this our data consists three types of variable: pressure, velocity, and strain rate. And also we can select which variable we want to display. So for example, I can remove strain rate and velocity to have pressure only, or we may choose velocity x component. So in this case, it's plus the value that x velocity on this line across the channel. So this is the xy plots. Um, okay, so next I can show you how to load the data of several time steps and realize the result by animation. So we can click this disconnect. It will unload the current data totally. So we can reload our data. So in this time I choose the simulation PVD. It will contains all the VTK files from all these time points. Apply here. So initially it display the first result of the first time step is controlled by here, this right corner. So in total we have 31 data, and it's starting from 0, and the initial time is 11 seconds. Then we can control how to display the results on different time steps. We can either play it together, so play it, so it will display the results on each time frame automatically. So in this case, we have only 31 time frames, and also we can choose display the first one or the last one, or step by step. And another view is that we can save this animation as a video files. So we can choose save animation. So in this way, it will play this flow field and save it as a video file. And here I can choose how many frames per second. Save animation and choose the format I want to save and give it name. And select the place to save it. Okay, maybe just here. It will change the size of window later to match the video format. and then we can actually watch this video. Yeah, so well, in this case, it's kind of very short because we only have data of 3 seconds. Yeah. Okay, I guess this is all I want to show you on this Paraview demo.